Alright, so today I am presenting to you about the calculus of bicycles. So the topic is just finding the velocity of the chainring itself with the radius of the chainring and the use of the brain. So that's just, and then from that you're able to find the distance traveled of that chainring and then of the wheel, but I mean, you don't need to go that far. It's just, this is the bike I'm going to get. I'm just going to flex on it. So, some background information. There's tons of different bikes and sizes, and I just chose a chainring that I had in my car. So it's a little bit bigger than normal ones that are in the back. But when you're pedaling and shifting in the back, the biggest ring is the one that's the easiest, and in the front, it's the opposite, just because of physics and stuff. They're all meant for different purposes and different kinds of bikes. So like on different styles and models, they have different sizes and numbers and all that just to fit the rider's style. And then I've got a little diagram of the drivetrain. So those are the chain rings or the front gears. This is the front derailleur. Got the crank arm, the rear derailleur, the cassette, and then obviously the chain. So that's basically how it works together. So for this, you just got to understand angular speed, which is how fast a circle rotates from 0 to 360 degrees. So from that, you're able to calculate the distance, if you have the distance of the thing, of the circumference, and multiply that by the angular speed to find the distance traveled. So example of angular speed is like the record. So this part here, if it's spinning at 360 degrees per second, this part out here is also moving 360 degrees per second. So it doesn't matter where you are on the circle, it's moving at the same angular speed all the way around. Another example is when two people are holding the rope and one person's spinning and the other person's on the outside getting thrown really fast. So then you also have to understand linear speed. So with that angular speed, so if this is spinning 360 in 1 second, this is also spinning 360 in 1 second, which is how far that travels. Like if you were to roll that out and put it in a straight line, that would be the linear speed, how fast that goes per second. So then how to find the distance from those, so I'm just using a 29er wheel as an example. So then you take the radius, 14.5 times 2 pi, which is the circumference of the circle. How you find the circumference of the circle, I believe. And you multiply it by the rotations of the cassette or the wheel travel. So that's just an example. So then you can find the velocity from the equation of the cassette that I found in Logger Pro. I converted it into barometric because you have that variable of time, so you need to make it into barometric. And then you take the derivative of those two barometric equations to find the velocity. And then I will use an example of the real cassette. So I took a chain ring, this is a cog, and I measured from here to straight across on the other one, because when the chain is on there, that's where the pin of the chain would be, so that's what I measured too. So then finding the equation for the cog, you just use x equals r cosine theta, or t, because it's in barometric, and y equals r sine theta, or t. So then, what you'll need to do on the quiz thing that I had is you take the radius, which is r, you put that in for r. So that one, that was my actual one, which is 2.875 inches. So I put that in for the r, and then you have to take the derivative, which is dx dt. So dy dt and dx dt, you can do them separate, and then you can divide them. So that'll give us the slope of the barometric equation there is how you do that. So take the derivative of these. That one is going to be 2.875 negative sine t, and then the y is going to be at 2.875 cosine t. So then it's going to be dx/dt and dy dt, and it's going to be negative just because it's moving in the opposite direction, so that doesn't really matter if it's negative or positive. So then here's my video. Well,
I can show you how to do it.
We'll have to do that afterwards, but to finish it up, so you do dy over dx, which is you just put that one over that one, and you put in the time, and you'll get how fast it is moving. So it's pretty simple there. Let's see if we can. All right. So then here's my picture of my measurement in Logger Pro and the points. It's hard to see, but they're inside